So here is a problem related to freestyle response question or long response question from kinematics, especially covering the idea of motion under gravity or motion under free fall. So let's see what we can learn from this. So it says a toy rocket is launched vertically upward with an acceleration of 3 meters per second square. The fuel runs out when the rocket reaches a height of 85 meters. So to illustrate this, we are going to draw a small little diagram. So we are going to launch a rocket from here, let's say location A, and it is going to accelerate upwards with 3 meters per second square because the rocket engine is controlling the acceleration. It's not 10 meters per second square downward, but 3 meters per second upward. Okay. So after the rocket reaches 85 meters from the ground, okay, the engine stops working. Okay, so here the engine runs out of fuel and stops working. Now what's going to happen is that, just for analyzing, rocket has already accelerated, so it's already have a velocity which is upward. This means it is going to keep on going upward, but the velocity will now start decreasing, right? So the rocket will keep on going upwards, but the velocity will decrease. Why? Because now it is under motion under free fall, right? Now the acceleration is downwards, which is at 10 meters per second square. Okay. So because of this negative acceleration, right, the velocity will decrease. So eventually, after decreasing, it will turns to be zero. So let's say at point C, the velocity at C is going to be zero, which means the rocket will stop there, and then probably the acceleration is going to pull it back, so it's going to fall back on Earth, right? So this is what the motion looks like. But now we come back to the question and see what they're asking us to compute. Okay. So it is saying calculate the velocity of the rocket when the fuel runs out. Okay. So in this case, we are going to focus from motion from A to B. Okay. From A to B. The initial velocity, right? U, V, S, A, T. We write like that for kinematics. Initial velocity is going to be zero. Just launched, right? Vertically upward with zero speed. And then it keeps on going. The acceleration is upwards, right? At 3 meters per second square. So the acceleration is positive at 3 meters per second square. And the height it reaches is given to be 85 meters. So S is also given to be 85 meters. Okay. And it is asking us to calculate the velocity of the rocket when the fuels run out, right? So we have to find the VB, and VB is unknown. Now we have three knowns, U, S, and A. So we can very easily find the value of VB, right? Ignoring T, time is not a concern. So the only equation which works very nicely is V square is equal to U square plus 2AS. We are going to use that to find our V. So U is 0. So it's going to be 2 into A is 3 and S is going to be 85. Okay. So let's calculate that, how much it is. It is 2 into 3 into 85. Okay. It's 2 into 3 into 85. That's 510. Okay. So 510, that's V square. So V is going to be root under 510. So we are going to find the root of 510. Yes. And that is going to be 22.6 meter per second upwards. Okay. This is going to be our answer for this one. This is 22.6 meter per second upward. Okay. Now, it is in the part 2, it is asking us to determine the maximum height reached by the rocket. Okay. So now we are going to focus from point B to the C and see if we can calculate how much is this height. And when we are able to calculate this height between B and C, we are going to add 85 to that, and that will be our maximum height, right? For maximum height, we'll have two parts, right? It will have 85 plus the height between B and C, right? So we already know 85, so let's focus on B and C. So at B, the rocket is already going upwards with a velocity, which we already found out was 22.6 meter per second, or V square was 510. Okay. From here, we keep on going upward, and the final velocity, right, velocity of C is going to be 0. Okay. So if we write our u, v, s, a, t, right? My u is going to be 22.6, v is going to be 0, and the acceleration this time will be downwards, right? At 10 meter per second square, so we're going to say minus 10. So now we know this three, u, v, and a, and what we have to find is the height, s. Okay, so this is unknown. Again, the time is not of a concern, so we are going to use our same equation, which is v square is equal to v square plus 2as. Final velocity is 0. U is square, we already know the value of u square, 510, and minus 2, because this is minus, so I'm just saying, so 2 into minus 10, 20 into s is what we have to find out. Okay, so my 20s will be equal to 510, and s is going to be equal to 51 by 2, and that is going to be 25.5 meters. Okay, so we have found this s here, or HBC, which is 25 meters. So my maximum height is going to be 85 plus 25.5 plus 25.5, and that is going to be 110.5. Okay, so 110.5. So the maximum height reached by the rocket, part 2, is 110.5. Now the part C, they are asking us to draw a graph showing the variation of the velocity of the rocket. Okay, so let's try that. So this is our graph. And as you know, the motion is actually in three parts. So we'll try to break that down into three parts. The first part is when the rocket starts from here and arrives here with a particular acceleration, and thereafter it goes from B to C upwards and then comes back down, right? So we're going to call it 0, or location A actually, right? For this time t. So first, the rocket is going to accelerate from 0, right? With a positive speed or acceleration of 3 meter per second square, which means we'll get a VT graph which will be sloped positively, something like this. Okay, so now it will arrive at some velocity here, and now the acceleration becomes minus 10. Okay, so we have arrived at B, so we are going to call this time B. Okay, this is our location B, okay, or time at B. Okay, this is our time at A, which is 0. And what is the velocity it achieves at B? We already know that, right? We calculated what is the velocity of the rocket when the fuel runs out, 22.6. So this is going to be 22.6. Okay. Now the object is at B. Now from here, it will start to deaccelerate and come to C, where the velocity will become 0, right? Now it is going to deaccelerate fast. So if this is 3, our acceleration is going to be 10. So it is going to deaccelerate fast. And now this is our time at C. Here, our velocity becomes 0. Okay, so we are at the top now, right? The velocity becomes 0. And from there, basically, it is going to accelerate at 10 meter per second square downwards. So keep on accelerating. The acceleration remains the same. And then the velocity will start to become negative, right? And sometime we're going to find what that velocity will be, right? And this velocity we have to find. But this is how it looks like. So how much time between TA and TB? We can compute that. How much time it takes from TA and TB. So part A, yes, part A. Here we know U is equal to 0, etc. And my final velocity is 22.6. And we can find the time. We can simply use V is equal to U plus AT. My V is 22.6 and U is 0. And the A is 3 into T. So my T is going to be 22.6 divided by 3. Okay, so that time is from TA to TB, which is, it looks like 22.6 divided by 3, and that is 7.5 seconds. Okay, roughly 7.53 seconds. So TA and TB is 7.53 seconds. Okay, you can also find TB to TC. Okay, TB to TC in the second part here, when we are concerning the speed of the rocket. Now this is B and this is C, right? So final velocity C is 0 and V is 22.6 or U is 22.6, right? Can we find T? Yes, using the same way we can find V is equal to U plus AT. My V is equal to 0, U is equal to 22.6. Now the acceleration is minus 10 into T. This will go on that side. So the t which we'll get is 22.6 divided by 10, which is going to be 2.26 seconds. Okay. Now this distance is 2.26 seconds. Okay. As you can see, this is a higher acceleration. We'll come back to this, that how much is the velocity. We can compute that as well, right? From the top, let's see, from the top, when the object was right at the top here, right? And then it comes down and basically covers a distance of, we can write that down, right? So right at the top, my initial velocity is 0, right? My s, which is now downward positive, how much distance it has traveled, the maximum height reached is 110.5. We have 110.5. My acceleration is now downwards at 10. Okay. With that, can we compute how much time it will take from TC all the way to A? Yes, we can. We know 1, 2, 3, and we can compute T. So in this, the B is missing, so we'll use S is equal to UT plus half A T square. Okay. So S is 110.5, U and T is 0, so it's going to be half, A is 10, that's T square, right? So that's going to be 110.5, right, divided by 5, so that's going to be T square, that is the time between C and A, is 22.1. We are going to do the square root of this. Okay, so square root of 22.1 is 4.70 seconds. Okay, this distance from here to back to this location is 4.70 seconds, right? We can find the final velocity as well. Okay, so final velocity we can find out using, so we now know U, S, and A. Okay, so with regard to T, we can directly use our equation B square. It's going to be U square, which is 0, right? Plus 2 into A, which is 10, and S is 110.5. So that is going to be 200 into 110.5, right? So that's going to be 110.5 and into, sorry, 20, right? Into 20. So that's going to be 2210, and we need to find the square root of that. That is going to be 47 meter per second square, right? So that's 47 meter per second. Sorry, 47 meter per second, and because this is downwards, it's negative. So this height from here to here is 47. Okay, so that's the way we can do the VT graph. It's asking in the part C2 is the position of the rocket from the launch until it reaches the maximum height, right? So how the position will change till it reaches the maximum height. That's fine. Position time graph. So for that, we have S, T, and we have to draw the position time graph till the time the object reaches the maximum height, right? So we know how much time it is going to take the object to reach the maximum height, which is here 7.53 seconds. Okay, so this is going to be 7.53 seconds. The rocket is going to start right from the bottom, right? And then it will go 85 meters upwards, okay? And then the acceleration is going to change, and that acceleration is going to be negative, but will keep on moving upwards, right? So let's see. So first, we are going to draw that how it is going to start from 0, right? And goes to the place where the engine stops, the engine stops, right? Which is 7.53, right? So it is going to go a curved path all the way higher to 7.53. Okay. And then what is going to happen? Now it is going to deaccelerate, but the position will be upwards, right? So we are going to now get inverse parabola, right? So this is a parabola which is convex, right? So this is increasing, sort of showing a positive acceleration, right? Once the rocket actually reaches the 85-meter height, right? It has a higher velocity, but the velocity now will start to decrease, but the position will keep on increasing. Okay, so we have to take that into account. Now the parabola will be other way around. Okay, so it will be downward parabola, right, with a negative slope. It is going to keep on going up like that, and then the velocity will become 0. Okay, so this height is going to be 85 meters, right? And the maximum height which it reaches I think we computed that to be 110.5. Okay, and this was 7.53. And then more time passes to reach the maximum height, right? I'm going to explain my t-axis here, right? How much is that time? Another 2.26 seconds passes for the velocity to become 0. So this is 2.26. We can add that up to get the t. And this is how our position time graph will look like, right? Important point. This is a concave parabola, which is positive. This is a convex parabola, which is negative. Okay, showing deceleration. Now let's get to the next part. Next part, it says calculate the time the rocket takes to fall to the ground from the maximum height, right? So that's going to be easy. So this is our maximum height. From here, we have to calculate how much time it is going to take to fall to the ground. I think we did already calculated that when we were doing this, right? So that was, this was our maximum height, right? Maximum height or the zero velocity. And then we calculated it will take 4.7 seconds for the rocket to fall to the ground, right? So this is 4.7 seconds. Okay, so in this problem, we dealt with a motion which was happening in two directions, basically because of two different acceleration. One was positive and one was negative, and then we can see how the position time also graph behaves in that way when the acceleration changes from positive to negative, from like concave upward to convex downwards, but still the position keep on changing, and then finally the velocity becomes zero, slope becomes flat, and we calculated all the times using our simple kinematical equations.